All right, I don't know if any of you, probably most of you wouldn't have needed to, but I did go ahead and post the video from yesterday online, and we'll continue to do that. So if you find yourself in a situation where you do need to miss and you need to watch the video, make sure you just recognize that that will be available. And yesterday's is already posted, and I'll get this one posted after class today. So for the electric potential notes, we're going to finish with a quick review of where we ended yesterday. So give you a practice problem or two to kind of refresh your memory. We'll practice those for a few minutes. Then we're going to jump back into the AP classroom and watch a video. And then we're going to come back to the notes and talk about what about potential when there's multiple charges in different arrangements. And then once we get through that point, then we will we'll switch gears to that PhET activity. So, all right, so here is the warm-up problem for you based on what we learned yesterday. Put this down at the bottom so you can see it. So John and Finley, are you guys seeing the screen okay on your side with this question?
Yeah.
All right. John's quick with that thumbs up icon. I can't remember how to do it. All right, so go ahead and try this one out. See what you come up with. And John and Finley, if you want to type your answer into the chat, that'll work. Find a space where it's not covering over things. You're saying D as well. Looks like you're saying D as well. D. Is that a D? All right. Hopefully most of you are coming up with the same answer. It looks like most of you are coming up with the same answer. And so if we check out the equation for potential energy, it's the constant, Coulomb's constant, times the product of the two charges divided by the distance between them. And since all of that information was given, it's pretty much just a plug and chug option, which does prove to be D as the correct answer. All right. There we go. All right, so try this one. Slightly different information here. Potential energy of the two charges in the following configurations. We got some different values for the charges and the distances. Seeing a few people coming up with C. Quite a few choosing C here, both online and in person. And so again, we can put that in here. The trick here, and most of you I think recognized it, you don't use the 6 or the 7, but you have to recognize that that's actually a distance of 13 meters. Not too particularly tricky since they give you a visual there, but they may or may not give you an actual visual scale here. So it may not be as visibly obvious that the distance is 13 in a word problem. So just wanted you to recognize that. And last up on our warm up here, student is given the values below for a system of charges. What can the student say about the configuration? 2 possible answers. So here's just a reminder of the equation, but here's the information they're given. So this is one of those multiple correct ideas. Let's see if we can get everything out of the visual realm here. There you go. I'm seeing a couple of B and C votes online. Looks like you're saying B and D, Tiger? Is that,
Wait, let me see.
is that what you were voting for?
Yeah.
Yeah? He says with maximum confidence. You think B and D as well? Right. Let's talk these through. It sounds like we mostly agree on B here. So what's wrong with A?
Says they'll move apart.
What's wrong about that? Yeah, they have opposite charges. They shouldn't move apart. They should move together. So A is a pretty easy, cross that one off. How about B? What about that one? Or I guess we all agree that B is true, right? An external force must act on the charges to prevent them from coming closer. It's kind of almost the opposite of A in some ways. So A is clearly wrong and B is clearly right. So C and D. So C says decreasing the distance between the 2 charges increases the electric potential energy of the system of charges. So they should go together, right? They're attracted because of their opposites. So they should go together. And so will they naturally decrease their distance or will they not naturally decrease their distance? They will naturally decrease their distance. So if we move them closer together, we're not storing up any energy. We're actually letting them go the way they naturally want to go, right? We need to pull them against that to be able to store some energy into it. Does that make sense? So if we put them closer together, that doesn't store any energy. That actually lets them go towards their natural inclination. To make them store energy, we need to pull them against that. We need to do work so we can store energy. Because work is the ability to change the form of energy storage mode, right? So to store the energy, we need to do some work. So we would have to actually pull them apart. So C is not quite right. This is where it's a little tricky though, because if you just flat out look at the equation and only think about it mathematically, decreasing the R value, if you only think about it that way and don't think about the concept behind it, decreasing the R value seems like, oh, that should make the potential energy increase, right? And so if you just think about it mathematically, then you could trip up on C. But with energy, remember energy is a scalar. So you can't quite think it through that purely mathematically. You have to think about what's going on qualitatively, not just quantitatively, right? So a little bit of a tricky one there. And then D says substituting each charge with the same value but opposite signs. So you switch the positive to a negative, you switch the negative to a positive, will have no effect on the calculated electric potential energy. Well, that's true, because if still they're opposite charges, then that's still going to give you the same result. Right? And so B and D are indeed the correct answers. But C is pretty tricky, because if you purely look at it mathematically, it seems like that should make sense. So you have to think about it conceptually. They naturally want to get closer, so to store energy in the system, I have to do work to pull them further apart. Okay? So if we think about gravitational potential energy, I just had this conversation with my CP class today. If I take this box, it has a certain amount of gravitational energy right here, right? It's a certain height above the ground. If I pick it up and put it up on the top shelf, I've done work, right? I've applied a force through a distance, and now I've increased its gravitational potential energy, right? But I had to apply a force to move it through a distance opposite the direction that it would naturally go, right? It would naturally fall because of gravity, and so I'm applying a force against gravity. So to store work, to do work and store energy, we need to push it against its natural inclination. In this case, it's not gravity, it's the attraction that they would feel, right? So we have to do work to push against that attraction. Does that make sense? And then by doing work, we can store the energy in the system. All right. Let's go on, and I think that's the last one for the warm-up. Yeah, that's the last one for the warm-up. Okay, so let's switch gears now and watch that next video. We got things open everywhere on this screen here. Oh, shoot, I think I closed the, open it up again. Closed the wrong tab earlier. So, John and Finley, are you seeing the browser, or do I need to switch the share?
We can.
You might have to type it in the chat. My computer keeps saying low system resources, and you're real choppy coming through. You can hear it as well. Oh, you know what, though? I don't think I shared the volume, so I will go ahead and redo this here. Share the sound. Otherwise, I'm afraid you won't hear it probably correctly. Let me minimize this for a minute. Oops, boy, it took me all the way back to ground zero here. We're on unit 3. There we go. You want to go all the way down to 311, and it's number 6 is the one that I wanted to go through. This is another one of those zero watched. I thought this is a good one, and since no one's watched it yet, I'd like to share this together. So get it full screen. And here we go.
Hello, physicists. My name is Teresa Brudnick, and I teach in Rhode Island. Today, we are talking about electric charges and fields. Specifically, we're going to talk about uniform accelerations. As we've talked a little bit before, there are a lot of parallels between electrical fields and gravitational fields. And when we release charges in electrical fields, they do behave in a manner that is very similar to masses that are released in gravitational fields, assuming that the fields we're talking about here are uniform fields. So there are a lot of similarities here, but there are also a few notable differences. So before we start getting into the similarities, I want to take a moment to acknowledge those differences, and then we can talk about those uniform fields causing uniform forces that cause uniform accelerations. So I want you to take a moment, pause, and consider this situation.
All right, so give you a chance to read it through. We had a chance to read through the scenario. A few seconds just to think about what you think will be true about the magnitude and direction of the forces and acceleration.
So when we're looking at this proton and this electron in this uniform electric field, and we're thinking about the magnitude of force that they experience, both protons and electrons they're located in a uniform electric field, meaning the value of the electric field strength is the same everywhere in that field. They should experience the same amount of force, because if the electric field strength is the same and the charge is the same, the amount of force is the same. However, protons are positively charged and electrons are negatively charged. So the direction of the force that they feel will be in opposing directions. This is very different from masses and gravitational fields because we don't have negative mass, which means that when we talk about masses and gravitational fields, uh, you're not going to deal with things accelerating upwards in gravitational fields all on their own, the way that we will have negative charges accelerating against the field in electrical fields. So
All right, so any questions about the idea of how the forces would be that they experience? Makes sense that they would have the same magnitude but different direction. Okay, before we hear her spill the beans, what do you think about the accelerations? Tiger, what do you think?
The acceleration of the electron is probably going to be bigger because the proton is more massive.
Okay. Since they have different masses and F equals ma, then even though they experience the same force with different masses, they should have different accelerations.
same magnitude of force, opposite directions. I also want to think about the acceleration that these two charges experience. So while protons and electrons do have the same amount of charge, they do not have the same amount of mass. And according to Newton's second law, even though these two things have the same amount of force acting on them, the acceleration that they experience is going to be inversely proportional to the amount of mass that they have, meaning that the proton is going to experience a relatively smaller acceleration than the large acceleration that the much smaller massed electron is going to experience. So when we think about this, in uniform fields, whether it's an electric field or a gravitational field, uniform fields do create uniform accelerations. But when we think about gravitational fields, the acceleration in a gravitational field is equal to the gravitational field strength. But in electrical fields, the acceleration of those particles in that electrical field is related to the electrical field strength, but it's also related to the size of the charge and the mass of the charge. So those
All right, so a lot of times in AP Physics 1, we refer to the g value as just the acceleration, right? It's the acceleration due to gravity. And there's nothing wrong with saying that, but that's not the whole story. G actually is also a representation mathematically of the gravitational field that a mass generates. Okay, so if we're saying G is one way to represent a gravitational field and a gravity only, we can say, well, that's also the acceleration. But that's not true for electric fields. Electric field is E in this equation, and it's related to the acceleration, but it's not equal to. So I just want to make sure you're catching that difference, that in gravity, they're different terms, same value, right? We can call it the acceleration, we can call it the gravitational field, but it's the same value either way. And while it doesn't necessarily mean the same thing, by definition, it is the same magnitude. Whereas in an electrical field, it not only has a different meaning, but it also has a different value.
are our two big differences there. So let's practice. Here we see four particles within a uniform electric field, and I want to rank the acceleration of these charges. So if I'm thinking about this, the acceleration that these charges experience is going to be equal to the electric field strength, which is the same for all of them, times the charge divided by the mass. So the thing that's different here is the charge to mass ratio. The larger the charge to mass ratio, the larger the acceleration is going to be. So this ranking is essentially a ranking of charge to mass ratio. Object B has the largest charge to mass ratio. A and D have the same charge to mass ratio, and then C has the smallest charge to mass
And
ratio.
before we go on to another example, any questions about that one? She went through it pretty quickly. Did you have a chance to absorb what she was saying and make sense? Electric field is the force to charge ratio, which then the acceleration would be that charge to mass ratio, since the field is constant. You're tracking that okay? All right.
I want you to pause and answer this question.
All right, so four positive particles of identical charge and mass interact with an electric field. At the time shown, all particles are located the same distance from the negative plate, but all have different velocities. Rank the time it takes the particles to reach the negative plate from most to least. Think this through for a little bit. right, so Ian, tell me one thing you know, even if you're not ranking them or anything yet. Just tell me as you read this question, as you think about what's going on, just tell me like a fact or something you know as you look at this situation.
Like, what do you, I don't really like.
I'm not looking for any specific, you could say a dozen different things. This is what, like, as you read this and as you think about it, what's something that you would consider that you would think is important?
Like the C and D already have like velocities pointing towards the sides of the plate,
Mm-hmm.
so it's probably gonna make them get there slower or faster.
Okay, good. Bob, what's something else as you look at this scenario, another factor or something you would want to think about to answer this question?
They all have different velocities.
Mm-hmm.
And they have identical charge and mass.
Mm-hmm.
Just underlying x.
Okay. Sean, anything else that you would add, something else that's important to consider here? Or just like a fact that would help you determine your final answer?
They have different positions.
They do have different positions. They're all the same vertical distance from the plates, but they do have different horizontal positions. Will the horizontal position matter? That's a good question to ask. Does the horizontal position matter for this question?
No,
Yeah, it won't matter for this one. Jason, anything else you can think of that kind of helps you process this?
Well, I mean, you know that they're constant particles, so you know which direction you want to go, which one get there first between like C and D.
All right, so which way are they all going to go?
Yeah.
Tell me.
Okay, because they're all considering it attracting to the negative, so
Good, good. So, David, give me something about the ranking, even if you don't rank all four of them, just tell me something you would be able to conclude about how they'll rank. Like maybe which one's gonna get there first, which one's gonna get there last, anything like that, just one thing you think you could conclude. Or if you're not sure, it's okay, you can just say that.
D getting first.
D getting first, okay? And give me some rationale for why you would conclude that.
Because the velocity is toward negative.
Okay. It's gonna be moving to the negative because of the charges and it's already moving that direction.
Yeah.
Okay, good.
Then,
Go ahead.
then B.
Then B?
Yeah.
Okay, and why is that?
Everything. Are A and B the same?
What do you think? You tell me.
Because it's kind of like the two-dimensional force. They don't have, on the y-axis, their initial force or velocity are the same.
So you say A and B will reach at the same time?
Yeah.
Okay, good. Will it be before or after C?
Before C.
Okay, good. How many agree with David's conclusion there? Very good. You guys did a nice job.
In this particular case, all of these particles have the same charge and they have the same mass and they're all located in the same electric field, which means that all of them experience the same acceleration in the same direction. So the time that it takes for them to reach, talking about an acceleration in the y direction, I'm really interested in what the initial velocity in the y direction is to help me determine time. Particle C has an initial y velocity that opposes the acceleration that it's experiencing, meaning it's going to take the most time because it has to slow down, turn around, and then accelerate from rest back towards that negative plate. Objects A and B both have an initial y velocity of 0, meaning they are accelerating from rest towards that negative plate. Object D is already moving in the direction of the negative plate with an acceleration in that direction as well. So it is going to take the least amount of time to reach the negative plate. Why don't you pause and answer this one?
All right, says a particle of charge positive Q and a mass m enters a vertical uniform electric field E so that its initial velocity v is perpendicular to the field. Determine the horizontal distance the particle will travel before making contact with the bottom plate. What AP Physics 1 style of question is this like?
Slick split.
Yeah, it's like projectile motion, horizontally launched projectile, right? So John, we'll see if the microphone connection works okay here, but give me some thoughts. What as you try to process this question, what are some things that are running through your mind?
Like what was said earlier, like how the acceleration is like the charge to mass ratio, and you can use that to find that acceleration towards the negative plate.
Good, good. Finley, anything else that crosses your mind as you think through this problem?
You said like relating to physics one topics, it kind of reminds me of the Cannon problems.
Mm-hmm.
Because you're just like the time it's gonna be.
Yeah, we're gonna have to find the time so we can discover the range. John, here in the room, any thoughts from you? Something else that strikes your thinking as you're going through this, or?
Yeah, I agree with what's been said. And I was reminded of the kinematics equation, specifically the one like with displacement, and they could cancel out the y component. So, I don't know. And those equations, math actually isn't relevant at all. It's just lost in time. So.
Yeah, yeah, in those equations, we didn't have to think about mass to figure out the acceleration, but here we're gonna have to have a little bit different strategy like other John was saying a minute ago. Anybody have any kind of conclusionary thoughts? We've talked about theory here and what things we need to consider. Tiger, do you have something?
Yeah, actually, did they give us the distance from the charge to the bottom plate?
Yeah, that's what I was
They haven't given us that distance.
Kind of necessary.
What were you gonna say, Ian?
I was just gonna, I mean, you just need to find like the time it's gonna take it from the vertical to fall to the plate, so. Yeah, I mean, you just need to set up like the kinematics, I think, to solve for that, and then you can just do the distances velocity.
All right. All right, so let's see her approach. You guys have come up with the right logic. You're thinking right down the correct track, processing exactly what you need to process.
So this is a glorified horizontal projectile motion question. This charge is going to follow a nice parabolic path as it goes through this particular electric field because there's a uniform electric field that's exerting a force in the downward direction, causing a downward acceleration that's constant, while that horizontal velocity maintains a constant value to the right. If I want to know how far it's going to go horizontally, I really just need to take how fast it's going sideways and multiply by the amount of time that it takes to reach the negative plate. Now, to reach the negative plate, I need to worry about what's going on in the y direction. So I'm going to use a kinematics equation with my change in y displacement, initial y velocity, and 1/2 at squared. Keep in mind, we are going to have to calculate the acceleration of this particle in this field using EQ over m. Plugging that into the equation and solving for time, then take that time and substitute it into the original equation that we were using for the horizontal displacement. So we're going to take that velocity, multiply by the time that we solved for, and that'll give me an expression to solve for how far sideways this goes.
This is one of those, no numbers, they want you to derive the equation based on taking other ones you already know and manipulating it. And this is like you're, I think, seeing more and more in this class. You really need to have AP1 before you can take this class because you need all this prior knowledge. And had a lot of students say, well, can't I just take AP2 first? Like, no, you really can't. But the other thing is that just like in AP1 where you're using energy and kinematics and dynamics and all things integrated into an FRQ, this is taking stuff from AP1 and AP2 into an FRQ kind of a question. And a very traditional college board, hey, we're not going to give you any numbers, but you need to derive a relationship, you need to derive an equation. Any questions about that? Does it make sense as you see it worked out? All right.
Actually, go to the bathroom real quick.
Anybody come up with that? I know I didn't give you a whole lot of time to do the algebra. Anybody have a chance to come up with that, or? Oh, you did? Did you get the same relationship?
Yeah,
Okay.
yeah.
Good.
All right, once more with feeling. When we're dealing with charged particles in uniform fields, you can calculate the acceleration of that charged particle by taking the electric field. Once you have the value of that acceleration, because that's a uniform acceleration in a uniform field, you can essentially just do kinematics with it. Thank you so much for joining me. Stick around for our next couple of videos in which Ms. Basiaga is going to be talking to us about isolines. Until I see you again, please be safe and make good
Really
decisions.
slow today. All right. So that was, if you're keeping track at all, that was number 6 and 311. There's one more that I want to show you next week, but we'll wait until Tuesday, at least one more. These videos on isolines are pretty important. So I'd highly recommend, I don't know that we're going to take the class time to watch them, but they are highly important. So if you haven't watched those 312, there's only 3 of them on isolines. We just briefly mentioned them. I haven't seen it to be a particularly, like a super frequent question, but I still would be familiar with it. We might take a look at one of them. We'll look at some examples and problems that involve it, but we're not going to take as much class time on that. But we will look at one of these conservation videos to wrap it up next week. So, all right, let's go back to our notes. So, John and Finley, are you seeing these notes okay? Okay, good. All right, so now how do we deal with electric potential energy when there are multiple charges? So to get the total potential energy for multiple charges, you must first find the energy due to each pair of charges. Then you're going to add those energies together. Good advantage, energy is a scalar. There is no direction involved for scalars, so they do have positive and negative values assigned with the charge that's present on each pair, but it's not directional. So if we have 3 charges, then we would find the total potential energy of the system by taking the potential energy from object 1 to 2, object 2 to 3, and object 1 to 3. So you can see the subscripts there, where the subscripts, and as abbreviated the bottom line there, x and y, are just telling you which 2 objects you're comparing at a time. All right? Any questions about that thought process? See a few people writing some things down there, so I'll give you a little time. I'm not sure I would say this equation is necessarily one that you would for sure want to have in your equation list per se, but you definitely want to have this concept in your brain. You want to be able to think through that this relationship works. So, and it doesn't just have to be 3. They're just giving you an example of 3 here. You might need to look at a situation with 3 or 4 or however many. Typically 3 and 4 are the most common. Either a triangle or a square kind of a shape is generally what you see in the questions that I've reviewed so far. All right, so that's the overall approach. So now let's look at an example of that. It says compute the electric potential of the 3 charge configurations. So we've got Q1, Q2, Q3. So there's a distance from 1 to 2, a distance from 1 to 3, and a distance from 2 to 3. There are no values for the distances between the charges or for the charges. It's all just variables. So we're looking for an algebraic derivation kind of a thing, that kind of a solution. Quick notation review. When we see a subscript 12, it means 1 to 2. It doesn't really mean 12. And here's that, again, equation relationship we saw in the previous slide. We're going to need to add up the 3 potential energies based on the 3 interactions. So I'd like you to pick a partner and get a whiteboard and see if you can figure this out. So grab a partner, grab a whiteboard, see if you can come up with this algebraic solution. And for John and Finley, I'll put you guys in a breakout room so you guys can discuss it. Yeah,
How simplified do you want it to be?
as far as you can.
Oh, okay.
Oh, it is? So it's not a. Oh, I remember.
I remember like that format of it.
Yeah, you would know.
I feel like it's more to write. You have to write more. Well, yeah. Does that matter? It's fine. It's simplified. It's in the most simple 11 for this. It's only do 9 for that.
Can I draw this for you?
I need a perfect round.
Yeah, that's his stuff.
You expect. Loving memory. Big tip. Yeah, just
I mean, it's you kind of just like I mean, like the best thing. Is there anything I could do here? I have to know. Are all the charges positive? Actually, no, that doesn't matter. If it's negative, it's automatically negative.
Yeah, me.
Or I mean, is there?
Right.
Yeah, it's automatically negative.
You guys come up with a solution?
Yeah.
Okay. You guys come up with a solution back here?
I'm telling you.
How about you, Ian?
Yeah, we have a solution.
You got it? All right, let me pull them back from the breakout room here.
You should have won this room.
Oh yeah, that one is actually good. That looks exactly like
So John and Finley, were you guys able to come up with a solution?
Yeah.
Okay, good. I think we've got, everybody in here has some kind of a solution as well. So I'm gonna reveal what they came up with on the slide, and then I want you to compare what you came up with and see how they compare. Let me know if you have something different that you think is more or less valuable. Either way. All right, so here is their process. They've just used the basic formula, and they've isolated out the K. All right. Anybody have any anything different or like drastically different? Did you guys get a common denominator?
Yeah. We simplified it more.
Yeah. Anybody have any questions about that? I love how they conclude the slide. It's that easy. You should always solve physics problems algebraically first. It shows you understand the concepts and makes the math easier. I don't know that I always agree with that. It is what College Board always suggests, though. College Board does always suggest solve it algebraically first. I feel like it depends on the question. Sometimes, in fact, today, just in AP1, we were doing a electric force, gravitational force combo question. And one of the students did solve it algebraically, and almost no one in the class understood what she was doing, because it was kind of an algebra geometry solution. It was really well done, but most people just couldn't follow it. And so there are times when I agree with what they're saying here, but I think there's other times when I showed it in just a quick step-by-step instead of solving it all first, and almost everyone in the class like, oh, okay, that makes sense. And so I think it depends on how your brain works. You know, sometimes that might be the best thing. I have noticed like David tends to do that. David tends to solve them algebraically first. For him, that works well. And so if that's the way your brain works, keep on trucking with that. Like that's a good strategy. That's what College Board even suggests. But if you find that difficult, while they do recommend it, if it's harder for you and you're more likely to make mistakes, don't do it, right? I mean, do what's best for you. That's my opinion. All right, so the K was factored out, so you only have to multiply it one time, saves calculation steps and reduces errors. Other than that, going to the extra step of finding a common denominator, no problem with that. It doesn't make the problem any worse or better. It might take a little more time to do that. I don't know, maybe not, but yeah, that both would be fine. All right, electric potential energy of multiple charges. What if we keep all the Q's the same in terms of their value, and we keep all the distances the same, but we flip where the Q2 is, so we change the shape of the triangle that way? Would the potential energy of the system be the same or different?
It's the same.
Same, the Q values are the same, the distances are the same, so there's no change in the potential energy of the system. They're pretty emphatic about that. No, unlike electric force and field, electric potential energy is a scalar. As long as the charges and dimensions between them are the same, the potential energy stays the same. So we don't have to worry about the direction and using that trigonometry to find those components with energy, which is one of the nice advantages. All right, so let's try a couple practice problems. If you have the whiteboard still and want to do it on the whiteboard, that's fine. If you just want to crunch it on your calculator, that's fine. But let's try a couple here just to wrap up, and then we'll jump into that PhET simulation. Yeah, if you have it, it actually makes it kind of nice.
No, it's actually not very. I think it's used for normal thing, because this is. Yeah, it is.
And again, John and Finley, whenever you guys come up with your answer, you can just type that in the chat for us.
Close enough. 4.9 something.
Did you guys use your form?
No,
No?
it's too many numbers
You
to
have
type.
to, yeah, you have to type in 11.
11 instead of 9.
Instead of 9.
Yeah, I used it, it did not work.
So did you use the one that they had? I didn't see yours. Ian, was your formula that you guys came up with, was it just like what they had, or?
Yeah, but we just didn't factor out the K.
Alright, and then David, I didn't see yours either. Did you have it just like they did, or?
Yeah.
Okay. Seeing a few people starting to get some results in here. As some of you are still plugging and chugging some numbers through, just a general question, do the signs matter? Do the signs matter?
Yes. Yeah,
Yeah.
yeah, they do.
When do they matter in terms of the formula? In other words, does it matter for the charges, or does it matter for the distance, or does it matter for both? In terms of using your formula. What's that?
Oh, I didn't say anything.
Oh, okay, I thought I heard.
Like it matters for the charges and then distance is just always positive.
Yeah, the distance is always going to be an absolute value. So while the charge is important in terms of figuring out what the distance is, you're never going to have a negative distance value.
Oh, I know.
But it does matter for the charges, right? You do need to make sure you keep those negatives in there, not because they're vectors, but just because it tells us about the value of the charge on the particles or on the points. So I'm seeing a few people getting B. Here is the strategy that they're using. So just finding this relationship for 1 to 2 is negative 4.05 times 10 to the 4th. From 1 to 3, 1.02 times 10 to the 4th. From 2 to 3, negative 1.69 times 10 to the 4th. And then we add them together. And they just added them with the exponent, the scientific notation portion out here. And got negative 4.72 times 10 to the 4th joules. All right, and let's try this one, a little bit different take. Instead of in a straight line on a number line, I think this is a little bit more common. How many have an answer so far? Got a vote for A. John and Finley are both voting A online. All right. Here's the strategy they're using here now. They're using that modified formula to illustrate it. So just factoring out the K value and seeing it that way. Adding them up, multiplying by K, and we get letter A, negative 305 joules, 3.05. All right, more of a kind of conceptual problem here. Three positive charges are aligned as seen below. They are not equal to each other, and the distances between them are different. They are replaced with negative charges with the same magnitude as the positive charges, and the distances remain the same. Does the electric potential energy increase, decrease, or stay the same? Justify your answer, not using an equation, but more of a verbal answer to it. I mean, you're thinking mathematically, but you're not gonna like try to write out an equation to prove it. They want you to talk it through conceptually. What do you think? Any ideas? Jason, you look like you had a thought right off the bat.
Yeah, it's the same because if all of the particles are negative, then the signs will cancel out anyways because they're multiplied with each other first.
Yeah. And you could even take it a step further from the math to say, if you have all positive charges, what are they going to do? Repel. And if you have all negative charges, what are they going to do? Repel. And if their values don't change, they're all repelling to the same magnitude, right? So you could think about it mathematically that they do cancel, but they're also wanting you to recognize that concept. So here's their phrasing of their answer. The electric potential energy of a system of charges is a scalar sum of the potential energies for each pair. The potential energy depends on the charge's magnitude and the distance between them. For all positive charges, you get a positive potential energy. For a system of negative charges, the pairwise products are also positive. So they kind of took Jason's approach there, mathematically thinking that through. Thus, the potential energy of each system is the same. All right. And last one. What factors are required to calculate the electric potential energy of a system of charges? 2 correct answers. What do we need to calculate the electric potential energy of a system? Got a couple votes for C and D on the chat. How about you guys here in the room? What do you think? Do you agree with C and D? I see some hand signals going up for C and D. And so we all agree, C and D, the distance and the sign of the charge are what we need to know. All right, so for John and Finley, we're gonna start this PhET simulation. So if you go to Unit 3, you should see, I can show you here on the screen, I guess might be easier. For those of you that are here in the room, I'll go ahead and set them out for you to grab. So it's just you're not gonna have to write anything up in your lab journal. I'm just gonna, it's counted as a lab grade, but you're just gonna fill in this document using the PhET as a simulation. So there's your paper copies. And then for John and Finley, let me just show you, make sure you find the right one here. So are you guys seeing the browser now okay? Good. All right. So if we go to topics, Unit 3, right down here, bottom right, there's the link for the PhET, electric potential and capacitance. And then here is the handout. And this is, hopefully it'll open shortly. And so for those of you in the room, you'll just need to get a computer, some sort of resource to get online. You're welcome to work with a partner if you want. You can work individually if you want. It's a lab, sort of, right here. you're gonna be looking at a capacitor setup and a dielectric and multiple capacitors. And the beginning it talks about potential, which is what we talked about today, and then towards the end it starts leading you into capacitance, which will be something we talk more about next week. So use this last 15 or 20 minutes here to get started on that. It is not due Monday. I just wanted to not give you notes the entire 80 minutes. So I want to give you a little time to switch gears a bit. So I'll put on, I think this will probably be due Thursday. So a week from today. I don't know that we'll have a whole lot more class time to work on it after today though.
He's BJ. He's okay, I don't know.